What if I told you that James Webb may have discovered a black hole that's bigger than the galaxy around it?
For decades, the story of our early universe has followed a specific sequential path. After the Big Bang, the first stars ignited in the dark. Gravity then pulled these stars together, clustering to form the very first galaxies. In this accepted model, black holes are the final step in the sequence. They are thought to form only when the most massive stars burn through their fuel and collapse. Under this logic, a galaxy must exist first to provide the stars that eventually become black holes. These black holes then settle into the centers of their host galaxies. Over billions of years, they grow into supermassive giants by feeding on the surrounding gas and stellar material that the galaxy provides. This established framework treats galaxies as the necessary incubators, while supermassive black holes are the evolutionary byproducts that arrive much later in the timeline. But the James Webb Space Telescope recently captured data that contradicts this progression. Deep in the ancient universe, Webb spotted an object existing just 700 million years after the Big Bang, a period when the universe was only 5% of its current age. This chart shows the signatures of a new class of objects astronomers call little red dots. This specific target, Able 2744 QSO1, shows a compact red-tinted profile that behaves differently than the standard galaxies we are used to seeing in the early universe. Initial indirect measurements of QSO1 suggested something unusual. It appeared to harbor a supermassive black hole that was far too large for the tiny host galaxy surrounding it. If these measurements are correct, they present a direct conflict with our current understanding of cosmic growth. It forces researchers to ask a difficult question. Did the black hole somehow form before the galaxy? Verifying this anomaly is difficult. QSO1 is over 13 billion light-years away. At that distance, even Webb's mirrors struggle to resolve a tiny host galaxy or the effects of a central black hole with high precision. To get a clearer look, astronomers took advantage of gravitational lensing. This occurs when the gravity of a massive foreground object physically warps spacetime, acting like a natural magnifying glass that brightens and magnifies the image of distant objects behind it. The team used a massive cluster of galaxies called Able 2744 as this magnifying glass. This cosmic alignment brought QSO1 into sharp enough focus for the telescope to gather direct data on its internal motion. This provided a rare opportunity to move past assumptions based on local galaxies and directly measure the mass of an object in the very early universe. Since black holes are invisible, the team tracked the hydrogen and helium gas swirling around the center. By mapping the motion of this gas, they could calculate the strength of the gravity pulling on it. They were looking for Keplerian motion, the same gravitational law that governs our solar system. In this pattern, the closer material gets to essential mass, the faster it must orbit to avoid falling in. Webb's spectrograph confirmed this motion. By measuring the extreme speed of the innermost gas, researchers could directly calculate the mass of that central point. The results were stark. The black hole weighs 50 million times the mass of our Sun. That single point makes up roughly 2/3 of the entire object's mass. In nearby galaxies, supermassive black holes typically account for only a tiny fraction of the total weight. In QSO1, the black hole is the dominant feature, essentially a supermassive black hole without a significant host galaxy. Because this black hole is so massive compared to its surroundings, it is unlikely it grew slowly through the deaths of early stars. There simply wasn't enough time or material in its immediate environment. One explanation is direct collapse. This theory suggests that massive clouds of pristine gas in the early universe collapsed directly into black holes, skipping the star phase entirely and starting their lives already at a massive size. Another theory points to primordial black holes, forged by extreme density and pressure in the first second after the Big Bang. Regardless of the exact origin, Webb's evidence confirms that this black hole was born large, rather than growing into its size over billions of years. These observations suggest that our understanding of the early universe's growth may be backwards. The black hole did not necessarily wait for the galaxy to form first. Instead, it appears that supermassive black hole seeds existed first. They acted as gravitational anchors in the early cosmos, attracting the gas and dust necessary to eventually build a galaxy. In this revised order of events, the galaxy actually builds itself around the pre-existing black hole. The discovery suggests these ancient black holes were the original architects of the cosmos, providing the gravitational pull that gathered the material for the very first galaxies. To see how else Webb is changing our view of the stars, subscribe for more updates from the deep universe.